Hello. So in the previous episode, we discussed the basic concept in reinforcement learning, and we know that there are a lot of different kinds of algorithms in reinforcement learning, and one of the fundamental algorithms in reinforcement learning would be the Q-learning. Okay, so basically, in the Q-learning, we simply set up a table for the action value pair, which is the Q value, and look up the table to find the optimal policy or the optimal action under each entry of the table. Okay, but that would be only possible for us to investigate the case where this state space would be discrete, or the action space, right? It would be finite or discrete space. So what if the states or the action space would be infinite? So it would be not available for us to use the Q-learning. So in the literature, later other researchers, they provided a new approach using the neural networks, the idea from deep learning, to solve this problem. Okay, so that new algorithm is called deep Q networks, and in short, DQN. Okay, deep Q networks. Okay, and DQN, and that solves the infinite problems. Okay, with the state or action spaces. Okay, so in this video, we'll shortly discuss this DQN algorithm and understand how it is working. Okay, so still here, we only have one single agent. Okay, and also the state would be fully observable. Okay, so we don't have partial observability here for the state. So those are just the basic setting, and this algorithm was already about like 10 years ago or so, right? So many years ago. So okay, so let's but that would be still very powerful and a very fundamental algorithm for us to understand. Okay, in order to further understand many other more complicated algorithms in reinforcement learning. Okay, so we still have single agent and fully observable. Okay, so this video will be in a way that very helpful for us to have a very straightforward understanding of this algorithm. Sometimes it's when we're looking at the papers and those equations, we don't really understand the meaning of those definitions or those expressions, right? So here, I hope that this video will be very helpful for us to understand those things. Okay, so this will be a single agent and fully observable reinforcement learning setting. Okay, so an agent observes the current state S. Okay, this will be the state on time step t at discrete time step t. Okay. All right. And then we say that this agent, after observing that, then chooses some action. So we use this UT, or sometimes we use AT. So either way. So UT. This is the action. Okay. And that would be according to some potentially stochastic policy. Okay. According to a potentially stochastic policy, pi. Okay. Of course, this agent will observe some reward signal RT. Okay, this is the reward. And the reward, to put it straightforward, so when we're playing some game, and such as let's say if we're trying to let a robot to avoid some traps and to avoid some dangers and to reach some goal on the let's say on the chessboard, in the two-dimensional chessboard, then this the state the reward could be after reaching the final goal. For example, if the robot catches the queen, then this robot gets a very high reward afterwards. But if the robot meets some trap on some blocks or meets some danger, then this robot gets a very low, even some negative reward. Okay, so those reward would be just a function. Okay, so we could treat those reward as some function of, let's say, of st and at. Okay, so given that the state is st, and if the robot takes some action at, then the environment will give this reward using the reward function rt, or returns this reward rt to this robot. Okay, good. So sometimes if we cannot actually, later we'll introduce the q function. Okay, but it will be just some value, action value function. But if sometimes we're difficult to solve directly to model those q functions, but it will be relatively simpler to model those those reward functions. Okay, because those reward functions are just deterministic. Okay, so if we know that the state and know the action, and we will certainly get some reward because we know how right, because the reward will be given to this agent for sure under those circumstances. Okay, good. So this is reward, and and also the state transitions to a new state, right? So st plus 1 will be the new state. Okay, so transitions to a new state. Okay, st plus 1. Okay, so here the objective of this problem, or for this agent, okay, is to try to maximize expectation. So what is the expectation? It will be the expectation over the discounted returns. Okay, max the expected discounted return. Okay, because we need a discounted factor for the future rewards. Okay, good. So mathematically, we can write this as big RT will be the summation of all those little RTs plus gamma, which is discount factor, times RT plus 1 and plus gamma square, RT plus 2, dot, dot, dot. Okay, so RT is the reward received at time t, and gamma will be just a discount factor. Okay. Okay. Good. So now, because this algorithm is called DQN, so what is the Q here? So this Q function, okay, is, so that would be a function of a policy pi. So that Q function is as follows. So this Q pi, if we have some state S, and we have this in the previous videos, right? So this would be the input for the current state and action for time period t, right? And this would be an expectation of those big RTs, the big RT of those little RTs, right? As we mentioned above. And given that the state for time period t, which is this little s, and the action in time period t, it will be little u here. Okay, good. So that's the Q function. Okay, so that's pretty straightforward. So we want to have this sort of the optimal function version of this Q function. Okay, so the optimal. Okay, so the optimal action value function Q or the Q function. Okay, so optimal version Q star given as in U. So now this will be just the max by choosing some policy pi. Okay, and in a way that this Q pi is maximized here. Okay, so and previously in the other earlier videos we have shown that this could be written in the Bellman equation. Okay, so a Bellman equation is just a very standard result from dynamic programming that help us to rewrite those object functions in the terms of current reward and future rewards. Okay, so that's it, nothing else, right? So let's see how do we do that. So using Bellman equation, so this Q star SU can be written into expectation, and that'll be expectation over the next state S prime. Okay, over the because that'll be unknown here, and we have this current reward R plus the discounted future rewards, and here the discounted future rewards also needs to be the maximum, right? Because we have this Q star, so this will be the max by choosing the next optimal action U prime to maximize the future rewards, right? From the next period onward, and this Q star and given S prime and U prime for the next period, and everything is given the current S and U. Okay, good. So this is the direct result from the Bellman equation. Okay, to rewrite the optimal action value function Q star. Good. So here we said that this is a called deep Q learning. Okay, so now we have this Q. So how do we implement this deep learning? Okay. All right. So now let's see how do we do this. So this deep Q learning is simply uses the neural networks. Okay, and we say the parameter it is parameterized by theta, or we use theta to simply know the parameters. Okay, good. So DQN are optimized by, okay, oh, we should have this data first, right? So DQNs, okay, maybe we should do this later. Okay, so deep Q learning, we introduce the data first. It uses neural networks, okay, to help us to deal with the infinity problem of those actions and states, right? Instead of looking up the tables. Okay, so neural networks parameterized by theta. So theta would be just the notation for all the parameters, the weights and the biases in the neural network, to represent this Q. Okay, so given S and U, and we have the theta as the parameter. Okay, good. So how do we optimize this neural network here? Okay, so that would be the next thing. So DQNs are optimized by minimizing this loss function. Okay, let's say for each iteration I, Li of this theta I, and it'll be an expectation over some so-called experience. Okay, so this experience includes current S, current action U, reward, and next state transitions to next state S prime. So this is the so-called experience. Okay, and this expectation will be just the mean square error, right? So here we have this yi, which is the objective, okay, sort of as the label in the normal deep learning problem, right? And this is denoted by DQN. And minus some output from the network, which is simply this Q, as U data, as defined above. Okay, so we're trying to minimize this loss, which is the expectation of this square of the difference between the two, between this maximum, between the label, which is the target, so-called, this is the called target in reinforcement learning, okay, and this Q, which is the real output. Okay, so we said that at each iteration little I, okay, so here this is called target yi DQN. So what is this target? And we have already defined that. Okay, so the target would be just the term inside of the expectation of the Q star, right? So the first term would be this reward, and we have the discount factor and maximize by choosing some U prime for the next state and for the next period. And here we have this Q value and taking this S prime, U prime as the input. And here we have this theta I, but we add a minus sign here, which is just some notation to denote that this is different from theta, okay? And we'll explain this later. Okay, so this is essentially constructing this label or this target by by sort of decomposing the current reward R and the future maximum future rewards, right? So the maximum of the future rewards is obtained by choosing, this is very important, right? By choosing some optimal action in the next state, in the next period, U prime. In this way, we obtain, given sort of this function, this Q value function, and taking this level of the action in the next state, which is U prime, to try to maximize this. Okay, and that is actually, you will see that in this algorithm, that is uniformly sampled from this is so-called the experience pool or this buffer, right? So we simply select some of those, but because if we select all those adjacent experiences, then there'll be a problem of correlations, okay? So simply uniformly select all those or sample of those experiences, which are the this thing, right? S, U, R, and S prime. And here, what we could obtain for this yi DQN for this target value, and essentially here we are looking forward, right? So here, when we're actually we're calculating this y DQN, this target value, we have some information in the future, right? So, namely, we have this all those kinds of different combinations of those U prime and S prime, right? Okay, so that is essentially could be regarded as where we could look into the future, and then we compare that to something else that we output with this vanilla or this plain Q function, right? Okay, so that's essentially the idea of this this loss function, right? So this is the target, right? Y DQN, and we said that this theta I, we have some minus sign, little minus sign here, in the superscript. So this is simply used for denoting that this parameter theta, that theta I minus, is just a different set of parameters from theta. Okay, so those theta I minus are the parameters of a target network that is frozen for a number of iterations while we update the online network queue. Okay, so in this case, this will solve the problem of converging and instability, right? If we have this theta as exactly the same as this theta, then the network is really difficult to converge, and the training process will be unstable, right? Okay, so let's have some note. Qi minus are the parameters of a target network that is frozen for a number of iterations. Okay, sometimes it's 5 or 10 while updating the online network queue. Okay, SU theta I. Okay. All right, so that's action U, and that is chosen from this queue. Okay, so U is chosen from queue by some action selector. Okay, okay, so here we implement some epsilon greedy policy. Okay, so that avoids some problem of for example, if the agent initially has something some action that brings a positive return, a positive reward, and then that avoids the problem of this agent is repeatedly to select exactly the same action as the initial one. Okay, so here we use some randomness to give this to the agent to avoid those kind of problem of repeatedly exploiting some certain actions. Okay, which typically implements an epsilon greedy policy, which is essentially the essence of the explore and exploit, right? That selects the action that maximizes the Q value with a probability, let's say, of 1 minus epsilon, and then randomly chooses randomly with the probability of epsilon randomly, right? Okay, so it means that sometimes it simply doesn't choose the one that maximizes the Q value, okay? And it's simply randomized to avoid some certain issue that we just mentioned. Okay, so and another thing that we need to address is this experience, right? And it is called by experience replay. Okay, so DQN uses this sort of experience replay. Okay, so during the learning, the agent builds a data sets So this is in the loop of the training, right? So building a data set of episodic experiences and agent is trained by, like we just mentioned, by sampling or uniformly, normally, right? Normally uniformly sampling many batches of those experiences. Okay, so normally this is to avoid the correlations between the previous and next state and actions. Okay. All right. So that'll complete the introduction to the DQN algorithm. And later, if we have time, then we could try to show the implementation in codes for the DQN. So here, the most important part would be this loss function that this agent is trying to minimize. So here, as we just mentioned in the video, so this YIDQN would be the target value that these that is the analog to the label in deep learning, right, or the ground truth, and this value would be just the output that we have, that we derive or calculate using the current network Q network. Okay, so here inside of this target value YIDQN, so we do not only have this current reward R, but we also have the discounted future rewards. So that'll be by choosing or by looking through or looking into the future for one step ahead. If we have those U prime, S prime, those values, then those will be helpful for us to calculate the correct or the value or the value that are maximizing this Q function one step ahead, right? And that'll be helpful for us to derive this target value or this ground truth, this label, for us to calculate the difference or the loss, right? So, and where do those value come from? So as we mentioned, we have this experience replay, and during the training process, then this builds a data set of those episode experiences, including all those values, right? So S, U, R, and S prime, and those will be helpful for us to construct this target value, and then that'll be the YDQN, and for this Q, and you simply calculate using the S and U. Okay. All right. Good. So this loss is actually a that's sort of the key idea or the essence of this updating or the learning process of this DQN, right? Good. So that'll be everything for this episode or for this video, and later we'll try to show other interesting algorithms in reinforcement learning, and also try to find time to implement those algorithms.